Lesson 5, Metrics for Evaluating Performance. Hello! In the previous lessons, we built a neural network, trained it on real data, set up weights, and chose an optimizer. Now it's time to ask a critical question. How do we know if our model is actually good? In other words, does it generalize well? The main goal in machine learning is not just to memorize examples from training, but to learn the general patterns and be able to correctly predict new examples that have never been seen before. This ability is called generalization. To measure this ability, we divide the dataset into three defined parts: the training set, on which the actual training takes place. The network sees the data, calculates the loss, and updates the parameters using the gradients. The validation set is completely separate from the training set and is used to assess the model's performance during training. Is the accuracy improving? Is overfitting occurring? Should we stop early? Test set, a closed group that is used only at the end to measure the model's true generalization ability. The test set is not touched during training. Usually, the common split ratio is 70% for training, 15% for validation, and 15% for testing. During training, we track two important metrics: the loss function and accuracy, both for the training set and for the validation set. These two graphs allow us to identify phenomena such as improvement or overfitting. The loss is a numerical value that measures the distance between the model's prediction and the true value. The lower the loss, the better the prediction. Note that the loss is a continuous metric and is very sensitive to large errors. In contrast, accuracy measures the percentage of predictions the model got right. The formal definition of accuracy is the ratio between the number of correct predictions and the total number of examples. Or in the following notation, accuracy equals TP plus TN divided by TP plus TN plus FP plus FN, where TP is true positive, TN is true negative, FP is false positive, and FN is false negative. But it's important to understand, a decrease in loss doesn't always lead to an increase in accuracy. The loss may improve even if the model is still making mistakes on the same cases. The reason is that loss has a higher resolution. It's based on probability deviations, while accuracy only checks if something is right or wrong. Now let's look at an example from the medical world. Suppose we developed a system to detect a rare disease. In reality, only 1 out of 100 patients actually has the disease. If the model simply predicts that everyone is healthy, it will get an accuracy of 99%, which sounds impressive at first glance, but it misses the single patient, which from a clinical perspective could be a disaster. This is a clear example of how accuracy alone is not a sufficient metric. To deeply understand the model's behavior, we use a confusion matrix for classification problems. In its simplified version, it's a 2x2 matrix from which important metrics are derived: precision, what percentage of the positive predictions were actually correct; recall, how many of the actual patients did we manage to identify; F1, the harmonic mean between recall and precision. High precision with low recall means the model is afraid to make mistakes and gives only a few positive predictions, but those are reliable. High recall with low precision means aggressive searching, even if it results in many false alarms. Additionally, the ROC curve, a prominent tool in classification problems, is a curve that shows the relationship between the true positive rate and the false positive rate across all possible thresholds. What is the threshold? When the model gives a probability, say 0.92 for a disease, we need to decide from which value we determine that there is a disease. In other words, at what value the result is rounded up to 1. Usually, a threshold of 0.5 is chosen, but in certain cases, we might try to lower it in order to identify more patients. The area under the ROC curve is called the AUC, area under the curve. This is an overall metric. When the AUC equals 1, we have perfect discrimination. When the AUC equals 1/2, it's like guessing, and when the AUC is less than 1/2, the model is actually predicting everything in reverse. Let's now look at the example with the following graph. In black, model A with an AUC of 0.75. In blue, model B with an AUC of 0.86. In other words, model B is better than model A. Finally, when a model predicts a continuous number and not a category, for example, temperature, an amount of money, or a sugar level, we use other metrics, MAE, mean absolute error, MSE, mean squared error, and R-square, coefficient of determination, which measures how much of the variance in the data is explained by the model. Let's also mention some additional metrics that are less common but important in certain cases. Balanced accuracy, which is the average recall for each class, and the Matthews correlation coefficient, MCC, which is useful when there is a severe imbalance between classes. Similarly, the loss functions also change according to the type of problem. In classification, we usually use cross-entropy, while in regression problems we prefer MAE or MSE. To sum up, accuracy is just a starting point for measuring the model's performance. Recall and precision allow for a more qualitative analysis of the predictions. F1 reflects a balance when both types of errors are important. AUC and ROC provide a broader picture across different thresholds in classification problems. In regression problems, we require different metrics that relate to continuous error. It's important to remember all metrics are calculated only on the test set, since we are measuring true generalization ability, not just the fit to the training data. In the next lesson, we'll see the emergence of overfitting and regularization.